if I wanted to draw this, then I'm going to have the -3, which is negligible compared to 112, and they're both negative though. Both negative, so be real careful there. So if this is our radial arm at the 120 degrees, then AR has to point back towards the pole instead of a positive reading would have been outward. So we have a very small value pointing back towards the pole there of 3. And then in the theta direction, we have a -112. Theta's pointing this way, theta hat, so we're going to go back the other way, a significant value compared to the 3. It's going to be 112 that way. Did that agree with what's in the book? Or
no,
not?
They've got the magnitude is 5 millimeters per second squared.
Who does? The book?
The book. And we get 112.04.
Okay, the book's wrong.
Okay, here's a question. Is R 300 millimeters when theta is 120?
Well, I think they told us that, didn't they?
It's given.
Yeah, they prescribed at this instant, the power screw's radius is 300 millimeters, 0.3 of a meter. It's about this far out.
It's not really clear in the problem wording
Okay.
to me, but if we wanted to call that
I'm
so,
assuming there's
okay.
Yeah.
absolutely no reason to use the theta equals 120. I mean, that makes sense to me from the beginning, that you wouldn't
Right,
use the angle
right,
at the point.
right.
but-
So you don't need the angle 120 on that. Okay. What I'll do is I'll check the online solution manual and just see where they made their error. Or if you guys went along with my work and we collectively made an error, I'll let you know. Okay? But I'll check that out. And so just to finish off the problem then, the magnitude has to be equal to the square root of this 3 squared plus this 112 squared for our magnitude reading.
Based on their answer, it looks like they wanted a theta to be something like 4 or -4.
Yeah.
Because that would have resulted in
With a
16
5.
plus 9.
Right.
And
Yeah.
so I don't see how that could be 4
Right.
though.
Yep. So I don't see an error here. You guys were watching me as I did it, so.
It's hard to make an error. It's just like, here's your values, plug them in.
Yeah.
It's like basically
But what is important for you also, besides just plugging in numbers and cranking it out here, is to have a sense of these directions, because this is really important that you understand what direction these things are. And some of the other problems that I've asked you to do, you have to find out the angle between the acceleration vector and the velocity vector. You have to find out the angle between, let me ask you this first. Why might it be useful for you to know the angle between the acceleration and the velocity vector?
know how much this thing's going to be changing the direction of its path.
Yes.
If that angle is real tight, then it's basically just going to keep going the way it's going.
Yes. Okay, so let me just hold my arm here and think about it for a second. Let's say our velocity vector was like my arm with the eraser. Okay, velocity vector pointing that way. We know that that's tangent to the path at the instant. And let's say that the acceleration is like this. Like this. What can you tell me about the behavior besides just these values?
Most of this acceleration is tangential.
Most of the acceleration is tangential. Good observation. Most of this acceleration is just a cosine component of that angle between them. So most of the acceleration is tangential, which means that particle would be significantly speeding up. What could you tell me about the path? If this is the acceleration direction and the velocity is this,
It's virtually straight.
it's very close to being straight.
Yeah.
Very close to being a straight path. There's not much curvature going on with that path at that instant. How much normal acceleration is there if the acceleration vector is pretty close to the velocity vector? Here's the velocity vector.
Very little.
Very little normal acceleration, which means that it's got a real flat, large value for its radius of curvature. Large value for its radius of curvature, which means it's very close to a flat, very smooth arc. Not tight. Okay. Any other questions from homework?
I'm a little curious about the Coriolis acceleration. I don't feel like I understand
Yeah.
what that physically is, though I can probably mathematically get to it if I needed to. But I
Okay,
imagine we're going
good
to
question.
that later.
What is this Coriolis acceleration term? So let me give you an assignment to do, say, over the next week. Find a nice day when the sun comes out. Go down to the park. Don't chase the kids away, but go down to the park where they have one of those merry-go-rounds. Okay? And get that thing rotating. Maybe a couple of you go down there. One of you turn it. You don't have to go fast. Okay? just get it rotating, and then stand up on it and walk towards the center. When you pass over the center, I mean, it's going to feel weird. You've probably all done this at some point in your life, okay? It's going to feel strange because you're moving radially. You'll move inward towards, let the radius comes towards the center, walk towards the center, and then walk right across the center. And when you get to the center, you might think, oh, I should just be standing here not feeling much. I'm just rotating. But you're going to feel a force that's to your left. That's to your left. You'll feel a force to your left. And that's the Coriolis. That's the Coriolis times your mass is the Coriolis acceleration term. Notice the direction of it here in the derivation. Where did I do the derivation? Here it is here. It's in, see that term, 2r dot theta dot? That term's in the theta hat direction. So if I'm moving radially, here's my merry-go-round. I'm walking across it, and I'm coming right here to the center, walking with an r dot, while this disk is rotating with some theta dot. And so I come right here to the center. It's moving at a constant angular velocity. That term is 0. But even at a radius of 0, this term is not 0. It's this your walking speed as you pass through the center times this omega, or theta dot. And it's in that theta hat direction. So it'll be to your left. Mm-hmm.
Does it have something to do with that? If you're increasing your radius, then your tangential acceleration is then increasing also? Or is that the r theta dot term?
Depends on how you describe, what's going on with r dot and value of theta. Theta dot could be negative, that kind of stuff. So it's going to be, you just usually rely on the mathematics or the physical sensation. The water going down the drain, or the reason the ocean currents turn a certain direction in the hemispheres is partially due to this effect. Radial motion on a rotating body. Yeah.
Well, is that the same effect as it's the ballerina when they put their arms up?
No,
It's inertia.
that's an angular momentum concept. Ballerina slows down, spinning, or the ice skater spinning. Move the arms out, slow down, bring them in. We'll get to that later in the
So like
course.
the weather kind of, like when you watch the weather channel and everything, that's showing the weather kind of circulates all over towards like the low pressure.
Yeah. Imagine this. You have solar heating of the gases in the atmosphere. That causes rise, lift, okay? So you've got this gas that's lifting from the heating, and at the same time it's on the rotating Earth. And that causes the patterns to kick a certain direction. And then we could get into looking at high pressure systems and low pressure systems, and the air wants to move from the high pressure towards the low. But as it moves from the high, the center of the high towards the center of the low, it gets turned because of the fact that we're on the rotating Earth. So just some basic fundamental, just pick up an introductory meteorology book. You folks will love it. It's pretty interesting seeing the way that stuff works. Okay, let's get back to this stuff because I got to get into three-dimensional. We're getting into 3D a little bit there, but we want to get into it a little more physically here. Any other questions first before we leave the homework that you've been working on? No? Okay. So let's go to 3 dimensions. Your book has defined, has laid out a set of axes in 3 dimensions for you that you see here. And I can even make that a little larger. What you need to be very careful with when you pick up a reference book and you start grabbing equations out of a book is you need to be very careful that you go back and in this kind of, if the problem involves 3-dimensional motion, you need to go back and see how they've developed their equations. If you open up your Anton calculus text and compare it to this text, you'll notice that they're dealing with a right-hand coordinate system, which I think all textbooks will do. But here you have the XY plane, and if you rotate from X towards Y with your right hand, your thumb would point towards K, positive K, or the Z-axis, as you see here. So it's a right-handed coordinate system, as all textbooks are. However, when you move into defining a point in space, this book does it a certain way, and for the most part, it's consistent with your calculus text. However, here's the distinction with your Anton calculus text. Notice angle phi. That is the angle where it's defined as being up off of the XY plane. You can see angle phi right here to get to the capital R vector. In Anton, they define angle phi coming off the positive Z-axis and sweeping towards the capital R. So the governing equations in this book would be different than what you would see in your calculus book if you're in spherical coordinates. There's an engineering reason here, and you'll see it in the context of problems. So I'll explain why it's presented this way. Okay. So let's look at this for a second. The book lays their axes out something like this for us. And what I like to do is kind of pick an arbitrary point. And to get good with your sketching, if you lay out a set of axes, something like that, then what you want to do is make sure you go parallel to those axes when you're trying to get a projection. Like if I'm looking for a Y projection here, I want to make sure I go parallel to that line. And then here's my X here. And then let's say I come on up to some Z location. So here's a point that could be very conveniently defined, X, Y, Z, in space. And we'll call this, coming from the pole, 3 dimensions now, up to that point, we'll call that vector capital R. Imagine that there is a bright light shining straight down from above. And let's imagine we put a rod in here so it would create a shadow down onto the XY plane. If there's a bright light up high, directly above this, shining down, then it would project a shadow from this capital R vector right down onto this plane that would lie right on this diagonal, wouldn't it? Anybody see that shadow down here? There it is, right here. And we call that little r. We like that. And then also we measure from the positive x-axis sweeping towards the y-axis, we measure that in-plane, xy plane angle and call it theta. that's lying down on that XY plane. Now, imagine that this point up here in space is in motion, 3D motion. 3D motion. It might be, this thing might be extending or contracting. I like to think of a hook and ladder truck. Driving down the road with the ladder up, and at the same time it's up, it's rotating vertically. It's also extending in and out, and it's also in rotation this way. Right? They don't do that because those are designed to be handled statically, pretty much statically. They lock the truck in place, park it, and then they lift their ladder and extend it and maybe slowly rotate. Okay, they're not made for a dynamic environment. Okay, but you can imagine this. Imagine having fun, keeps you awake while you're working on these problems. Okay, so you could have this thing extending or contracting radially. You could have it in theta rotation, and you could also have it in what they define as phi rotation, measured up off this projection plane, some angle phi, up, okay? So you get general motion of this point up here that we're studying. General motion of a point up here. In space, this position vector could be defined as xi plus yj plus zk. Pretty handy sometimes. And we could crank its derivatives out and pick up its velocity and its acceleration vectors. X dot I plus Y dot J, Z dot K, and X double dot I plus Y double dot J plus Z double dot K. Perfectly decent way to handle three-dimensional motion. But for lots of motion, like me describing that extension ladder truck situation, or it could be a robotic arm in a manufacturing process. Reaching down, grabbing something, picking it up, rotating over, inserting it into something, going back, doing it over again. Makes sense? And what you would want to do in the design of that robotic arm is design it so that the gripping force doesn't crush the object. It could be a little bulb, a lightweight glass bulb, or it could be some kind of a sensitive electronic device that you're picking up and inserting, bringing it over and inserting it. The other thing you may not want to do with a robotic arm is bring it up and accelerate it really fast to where it would damage the part that it's holding. So these are all design criteria. If you're doing something that's in this kind of motion in different ways like this, then this coordinate system may not be the best one to use. So what might be nice to do is to use polar, a three-dimensional variation on polar. Three-dimensional variation on polar. And the way we can do that is pretty nicely. We can come in here and define, yeah, this is going to become now a big R, and actually technically I should have called this big R right here, capital R, based on what you see in this picture. So in polar, the good news is it's identical to what we've just seen in 2 dimensions with one extra thing tossed in the works. Down here, imagine you have the motion of this big R going on. What we could do is we could come in down here and take its polar terms, which would be a little r, here's a little r hat. It's down on the xy plane, just exactly the same as we've studied. And there could be an r dot right there. perpendicular to it in this plane down here, perpendicular to it, is going to be an r theta dot. Now this is in the xy plane, even though it doesn't look like it in the picture. In the xy plane. That's laying right down there on this xy plane. And it's perpendicular to r hat, perpendicular to the r dot term. Okay? And those are our polar terms that we've seen. So we have r dot r hat plus r theta dot theta hat. But that's not big R. Well, I'm sorry, I put that in the wrong spot. I was talking velocity, wasn't I? I was talking velocity, so it needs to be down here on the velocity term. R dot R hat plus R theta dot theta hat. That takes care of the projection down on the XY plane. What about its position? The capital R's position in a polar format. Little r in the r hat direction. That gets it out to here. And then to get this 3D vector, what do you have to add to this vector? Z k hat. The time derivative of this first term is what we got here. We derived that last week. The time derivative of this r hat we derived last week, and all we need to do now is take the time derivative of this z k hat, which is just what? Z dot k hat. That's it. So the polar form is actually quite nice for describing spatial motion, three-dimensional motion. Okay, now we need to crank the derivative of this, which we went back over its components earlier today. And so we have the r double dot minus the r theta dot squared term in the r hat direction, plus the r theta double dot plus the 2r dot theta dot term in the theta hat direction, plus the time derivative of z dot k hat, which is just z double dot k hat.
So it's the fact, what if both angles are changing?
Doesn't matter, it's all built in there. Well, this angle is accounted for through the z value.
Okay.
Yeah, and the z, here's your z axis. This is distance z right here, shown right there. There's your z, right there. Yeah. Okay. One thing you want to keep an eye on here is where the right angles are when you're doing these kind of motions. Here's a right angle. Here's a right angle. Here's a right angle. Here's a right angle. Bunch of right angles in there. All right? Okay, so here's your rectangular form in your equations. Here's your polar form in your equations for the kinematics. And there's a third one that we haven't seen before, the spherical. The derivation of this would take us a while, and they don't even have the derivation of the spherical in this book. Usually put that in a slightly more advanced dynamics book. It's easy to find, the derivation though. But here's where it starts. Remember how polar started? It just started with RR hat up here, didn't it? RR hat. Spherical starts with the capital R vector being defined as being a radial distance from the pole, a distance from the pole here, in a direction that is directly outward from the pole, and that's capital R hat. So it's just capital R times R hat. That's where it starts. And you go, oh, I like that. All I have to do is tell you, now watch my arms here. I'm going to wave my arms around again. I meant to bring a straight edge with me and I forgot it. So here we go. Imagine that I tell you, let's say X is coming towards you, straight out. Let's say Y then is over here and Z is pointing up through the top of my head, right? X rotated into Y, right hand rule, Z upward, okay? So let's say that I tell you a prescribed theta, let's say 30 degrees. Let's say I tell you a prescribed phi, say 45 degrees. Everybody okay? Got theta defined and phi defined. And then I say go out there, half a meter. Okay? If I give you theta and give you phi, then you know the direction of capital R hat. And I tell you to go out there half a meter, and we've nailed that point down in space, haven't we? We've nailed that coordinate down in space. Okay? So I could give you a capital R, a theta, and a phi. And that would pin this point down just as well as X, Y, and Z would. Since I'm writing coordinates up here right now, why don't I, since I forgot earlier, why don't I prescribe this in the polar form? This is going to be your spherical form. This is going to be your rectangular form. And the polar form is going to involve little r. So let's say I said go out, let's say I say go out a certain distance in little r and give you a prescribed theta, say 30 degrees, give you a prescribed little r, and then give you a capital Z. That would pin the point down in space just as well, wouldn't it? Okay. So we could do it with little r, a theta, and a capital and a Z. So 3 ways of writing the coordinate in space. And then to derive, we've derived the rectangular and polar already. Actually, the polar is not called polar in this 3D format. It's called cylindrical. Cylindrical. Okay. Now in spherical, here's where it starts. Now think about the dynamics when we start cranking the derivative here. When we start cranking the derivative. It gets interesting.